Imagine pouring an entire residential swimming pool of ultra-pure water into this incredibly complex network of stainless steel tanks, waiting 2 full weeks, and getting just a single suitcase worth of medicine out the other side.
Yeah, it's wild when you actually run the numbers.
Right. Today we'll explain how the science behind transforming a microscopic cell's output into a purified, ready-to-inject therapy actually works, and how we map that out. It's not just, biology in a petri dish. It is a massive, complex plumbing, cooking, and scheduling puzzle.
It really is. We always focus on the microscopic science, right? The cells.
Yeah.
But the reality is, bringing these therapies to market requires this unbelievable level of industrial engineering.
Exactly. So welcome to our deep dive on product selection, design basis, and bioprocess route identification using SuperPro designer simulation software. And this is part 2 of 2.
Which is where the really fun logistical stuff happens.
Oh, absolutely. And before we get completely lost in bioreactors and mass balances, I want to mention something really cool. If you are listening to this and you find this level of bioprocess engineering fascinating, you actually have the opportunity to pursue master's or PhD research studies with Dr. Rama Yusvana or his colleagues at UTHM. You can work on various bio-based projects of your interest.
Which I highly recommend, honestly. Yeah. The industry desperately needs people who can conceptualize this whole logistical puzzle, not just the biology.
Right. So let's jump right into that puzzle. Say we know we want to make a monoclonal antibody therapy, a mAb. How do we decide the actual steps to make it? Why aren't biomanufacturing routes just made up on the fly?
Well, because making it up on the fly with a multi-million-dollar facility is a terrible idea. So process route identification actually comes from a mix of scientific literature and really strict industrial logic. It is never arbitrary.
Okay, industrial logic. Let's talk about mAbs specifically, which, just for context, are these targeted immune system proteins we use as therapies, right?
Exactly. And for mAbs, that industrial logic dictates 8 very specific phases. You always start with cell expansion, so scaling of your cells. Then you hit phase 2, the production culture.
Right, the main event where the cells do the work.
Yeah. And once that's done, phase 3 is the removal of cells and solids. Because, the cells are just the factory. They aren't the product.
Right. I always think of it like, imagine this. It's like a high-tech water filtration plant, but instead of just cleaning water, you are growing the filter and the water at the same time. You had to separate them eventually.
That's actually a great analogy. So after you separate them, phase 4 is high-selectivity capture. You grab the specific protein you want. Phase 5 is concentration and buffer exchange.
Which is basically swapping out the liquid environment, right?
Then phase 6 is impurity polishing, so catching any tiny contaminants. Phase 7 is viral safety. And finally, phase 8 is final formulation and bulk storage.
Okay, so that's the 8-step logic. But how does that actually look when you're modeling it? Like, walk me through the actual clean teaching route from the sources.
Sure, so the specific route inside the software is essentially 13 steps. Upstream, you start with inoculum preparation. Then you move to a seed train.
Which is just increasingly larger tanks to grow the cells, yeah.
Exactly. Then into the production fed batch bioreactor.
And just to clarify for everyone, fed batch means we are continuously feeding the cells nutrients, but we aren't taking any product out until the very end. They just sit in there cooking.
Yep, a big 2-week soup. So after that, you harvest. The route calls for clarification, usually a centrifuge. Then your downstream starts with protein A capture chromatography.
Because protein A acts like a magnet for antibodies.
Spot on. Then you do dye filtration and concentration. Immediately after that, you have to do virus inactivation, usually by holding the liquid at a very low pH.
Wow, okay. And we still have more purifying to do.
Oh, yeah. Then you run IEX polishing ion exchange chromatography. Then ammonium sulfate conditioning, which sets you up for HIC polishing or hydrophobic interaction chromatography.
So that's 3 different chromatography steps.
Right. Then a viral exclusion filtration step. And finally, your last buffer exchange and concentration and into bulk storage.
Okay, that is a massive gauntlet.
Right.
So far, we learned that making mAbs follows a really strict 8-step industrial roadmap that translates into a highly specific 13-step route in the software.
And mapping that route is just the beginning. The real headache is figuring out what's flowing through it.
Right, because now that we have the roadmap, what are we actually driving on it? Like, why should I care about the inputs? Isn't it just cell food, sugar and stuff?
You think so, right? But this part is essential to understand because a process isn't just a sequence of equipment. It is a massive interconnected network of material flows.
Okay, so what are the major inputs we have to model?
Well, yeah, you have your serum-free media and inoculum media for the cells, but then you have all the chemical buffers. The protein A, the IEX, the HIC columns, they all need their own specific buffers.
Right, because you have to constantly wash and prep the columns.
Exactly. Plus salts like ammonium sulfate, things like sodium hydroxide, phosphoric acid, polysorbate 80. And then you have the physical consumables.
Like the disposable bags and the chromatography resins.
Yeah, and the membranes. But the thing that usually shocks people, the biggest revelation in the source material, is the utilities. Specifically, the WFI, or water for injection.
Okay, I remember seeing this in the data. For Casey, what was the volume?
The WFI consumption is around 51,750 kilograms per batch.
That is insane. Over 50,000 kilos.
Yeah, that's like filling an entire residential swimming pool with ultra-pure medical-grade water just for one batch of medicine. And don't forget the air.
The air.
Yeah, the air use is also substantial. These cells are breathing for 12 days straight in a massive tank. You have to continuously pump in sterilized air.
Wow. Okay, so this is a major teaching point. In biopharma, when we say raw materials, we aren't just talking about the biological ingredients. They absolutely include massive amounts of utilities and disposable plastics.
Right. If you only model the sugar for the cells, your facility will fail immediately.
So far, we learned that the inputs are incredibly vast and include massive amounts of utilities like water and air, plus tons of consumables. Which naturally brings me to my next question.
What comes out the other end?
Exactly. If we are putting swimming pools of water and massive amounts of media into this 15,000-liter bioreactor system, what exactly comes out?
Well, from that entire 15,000-liter bioreactor broth, plus all those downstream buffers, the desired output is just about 48.6 kilograms of purified MAB bulk solution per batch.
Wait, really? We put in over 50,000 kilos of water, and we get out less than 50 kilos of product. Where does the rest of it go?
It's all waste.
All of it.
Pretty much. And modeling that is a huge part of the conceptual design stage. The software requires us to classify all this waste into 4 broad categories.
Okay, break this down for me. What are the 4 categories?
You've got biological waste, you've got aqueous chemical waste, disposable consumables waste, and product loss.
Product loss makes sense. If you run medicine through 13 different steps, you're going to lose some along the way. But what about the specific waste streams for the biological and chemical stuff?
So biological waste is mainly the solid waste from the centrifuge, the dead cells, and the spent media. The aqueous chemical waste is your used chromatography buffers, your wash buffers, pipe losses.
Oh, and I imagine a ton of that 50,000 kilos of water is CIP waste.
Exactly. CIP is clean in place.
Right, which is basically washing the industrial dishes without taking them out of the sink, right? Because you can't move a 15,000-liter tank.
That is exactly what it is. You blast water and harsh chemicals through the pipes to sterilize them between batches. All of that becomes CIP waste.
And you can't just flush that down a normal drain.
No, definitely not. In advanced facility cases, the design actually sends the biological waste and the CIP waste to a dedicated bio-waste collection and treatment unit.
Wow.
Yeah, it thermal treats it, basically boils it under pressure to make sure it's completely safe before it ever leaves the plant.
Okay, so far we learned that the final product is a tiny, tiny fraction of the inputs, leaving us with a massive, carefully categorized waste management puzzle. Which brings up a huge logistical question.
How do you design all of this before the building exists?
Yes. To design this puzzle in a software like SuperPro Designer, we need numbers. But how do we start designing when we don't have a physical facility to measure?
And that brings us to the power of assumptions. In conceptual design, assumptions are not weaknesses. They aren't guesses. They're absolutely necessary simplifications so you can build the math.
Okay, so what are we assuming in this specific map case, just to get the software to run?
We tell the software a few key things. We assume a 12-day fermentation time. We assume a 15,000-liter broth volume. We assume the cells produce a titer of 5 grams per liter.
And what about the waste? Do we just assume how much medicine we're going to lose?
Yeah, we assume an overall downstream yield of about 64%.
Oh, wow. So we just accept we're losing 36% of the product.
Right, it's the cost of purity. We assume fixed step yields, like the centrifuge is maybe 96% efficient, protein A is 90%. When you multiply those out across 13 steps, you land at 64%.
And we also have to assume the timings for those cleaning steps, the SIP and CIP.
Exactly. Steam in place before operations, clean in place after. Because all of that takes time. And that leads to the final, really crucial piece of industrial logic. schedulability.
Right, because if the timing doesn't work out, the whole plant breaks down.
Exactly. For our base case, the recipe cycle time is 14 days.
But wait, if the production bioreactor is taking 12 to 14 days just to grow the cells, but the downstream purification steps, the chromatography and filtering, only take a few hours or a day each, isn't that a massive traffic jam? Like your shiny, expensive downstream equipment is just sitting there empty most of the month.
You hit the nail on the head. That is the exact bottleneck. To fix it, designers use a strategy called staggered equipment.
How does that work in the software?
Basically, you add multiple bioreactor trains, but you run them out of phase with each other. So bioreactor A starts Monday, bioreactor B starts Thursday, and so on.
And they all take turns feeding into the exact same downstream purification line.
Precisely. It brings the overall cycle time of the facility way down, keeping the downstream equipment constantly busy.
But hold on, if you speed up the purification line like that, you're needing that 50,000 kilos of water and buffers way more often. How do you even calculate when to mix the buffers so you don't run out?
Well, doing it manually is a nightmare. That's why advanced models use something called pull-out logic.
Pull-out logic, what is that?
The software basically works backward. Instead of pushing fluid forward, the downstream equipment says, hey, I need 500 liters of buffer right now, and it automatically pulls that from the holding tank, which pulls from the prep tank.
Oh, that's brilliant. So the software just automatically calculates the buffer usage based on whatever the downstream demand is at that exact second.
Exactly. It completely dynamicizes the schedule.
So far, we learned that making a facility work on paper requires really smart, explicit assumptions and clever scheduling, like staggered bioreactors and pull-out logic to avoid equipment traffic jam.
It is a massive juggling act.
It really is, and it's been such a fascinating deep dive just looking back at the whole journey today. We started with that strict 8-step industrial logic route. Then we saw the unbelievable scale of the inputs, like using an entire swimming pool of water for injection.
Right, and dealing with the reality of all that bio waste.
Yeah, the shrinking act, getting just 48 kilos of product from all of that. And finally, seeing how stating explicit assumptions and using advanced scheduling is the only way to make the whole conceptual design actually work.
It really reorients how you think about medicine, and it actually leaves me with a final thought for everyone to mull over.
Oh, what's that?
Well, we spend so much time using software to perfectly schedule the plumbing, the water, and the tank around the biological constraints of these cells, right?
Right.
But looking forward, what happens to biomanufacturing when we start using AI to engineer the cells themselves so that their biology perfectly fits the constraints of the facility?
Oh, wow. No, that is an entirely different puzzle. We'll definitely have to explore that another time. I want to express my utmost gratitude to technologist Dr. Rama Yusufana for his enlightenment and his invaluable insights into the topics we discussed today. It was a real privilege to have you break this down for us.
The pleasure was all mine. Thank you for having me.
Check the summary link in the description. Stay curious.